Hello everyone, my name is Habibur Rahman. Today I would like to talk about viscosity type methods to solve variational inequality problems and fixed point problems. And the outline of my presentation includes introduction, main results, and some numerical results. My main area of research belongs to computational mathematics. And computational mathematics is a branch of mathematics that studies and develops various numerical methods solving mathematical problems that are complicated in nature and are beyond the human numerical capability. So, what are numerical methods and why do we need them? Numerical methods based on algorithms that use to solve or find the numerical solution of a problems, and we need them in two different situations. The first one, when we do not have an analytical solution or it's difficult to find an analytical solution. Um, when an analytical solution is exist and is possible to find, but it is difficult to compute or it is time consumed, then we refer to numerical procedures. My main topic is variational inequality problem, uh, and we have a convex set and inside a Hilbert space, and the variational inequality problem for an operator A defined as find x star in C such that this inner product should be greater than equal to 0 for all y in C. There are different types of condition on operator A. So we have strongly monotone operators, strictly monotone operators, and then monotone operators. Uh, and there are other two classes of operators, which is pseudo-monotone and quasi-monotone. And for variation and inequality problem, mostly involve these operators. Variational inequality theory is an important tool in economics, engineering, mechanics, and mathematical programming. And to find numerical solution of such problem, we use projection techniques. And um, in- and previously there are many projection methods to solve such problems. The first method, which is defined by Pollack, which is a projection method proposed in 1966, which is one-step method and is calculating the projection of xk minus alpha a of xk on a C, and we have alpha is called a step size, and we have a condition on alpha which is belong to the interval 0 and less than equal to 2 lambda over L square. Lambda is a uh, uh, parameter for strongly monotone operator, and PC is a projection, and L is a Lipschitz constant operator. This method used to solve strongly monotone operators. Then other method in 1976, which is called a two-step extragradient method. The advantage of this method that we relax the condition on operator A, and we take operator A to be a monotone, which is a bigger class than strongly monotone, and it is a two steps projection method, and the step size is bounded by 1 over L, which is L is a Lipschitz constant of involving operator. The geometrical interpretation of extragradient method, that we pick xk, then compute xk minus alpha a of xk, and then projection on a C. Then again, by using a yk, we got xk alpha a of yk, and then project again on the set C, and continuously we get the weak convergence of this sequence. Another method in 2011, Sensor produced this method and he relaxed the condition and he worked on the projection on a set. Instead of the projection on a set, he defined a half space and the second projection placed on a half space rather than a set C, which is easy to compute in most situations. So that's why this method is the modification of the previous method, and still this method used to solve monotone variational inequality problems. And the geometric interpretation of xk, and the first on the projection on a C, then we have a half space which is by denoted by T of k, and then the second projection on a half space which is xk plus 1. Then this method is our motivation, which is proposed in 2018, which is a combination of extragradient method and viscosity method, help to solve two problems. Solve the variation inequality problem, and a constraint is a fixed point set. So it is in method one, we take a subgradient method and viscosity method, and in a method two, we take uh, um, the Sung extragradient method, where zk is not a projection on a set, is just a linear combination of some elements, and then we have a viscosity method, so which provide the weak convergence, and this method also used to solve monotone variation inequality problems and fixed point problems. Then there is a question arise that can we extend the previous method in pseudo-monotone operators, and we use dual inertial techniques and viscosity techniques, and find a method which is uh, have inertial steps, and the speed of convergence is better than previous, and also have a step size which is independent of the Lipschitz constant. So our main focus to modify the algorithm one, method one and two. The first algorithm uh, is the dual inertial viscosity subgradient exagradient method, in which step zero we set our parametric conditions, and step one we calculate the first inertial step, which is where theta of k defined in equation 4, and then we have step two, which is a second inertial step, and where word theta of k defined by equation 5. After these two steps, we calculate the projection on a set C, and step 4 is a subgradient method, which is a projection on a half space. Then we use a viscosity term, which is xk plus 1 is equal to alpha of k, and f is the contraction here. And then step 6 is update the step size, which dependent on the uh, calculation of values of operator on different point like wk and y of k. This is a first algorithm, which is based on subgradient method. There is a second algorithm, which is a slight modification of the algorithm one. We have same step zero, step one, and the step four is different from the previous method, which is the Sung extragradient method, rather instead of subgradient technique, which is better than the previous one in some situations, and in some situation the previous algorithm better. We will evaluate this in numerical section. The condition for convergence, we take six conditions for to study the convergence of these two algorithms. The first, we need the solution set should be non-empty. The operator is pseudo-monotone, is Lipschitz continuous, and Shikuli weakly continuous, and mapping for fixed point is eta demi-contractive mapping, and we have a contraction which used for viscosity techniques. These two lemmas are important in to study the boundedness of the sequence. This lemma one first produced from algorithm one, and lemma two produced by using algorithm two, where we have z of k the boundedness for z of k and the solution norm square should be less than. These two algorithms are useful to prove the boundedness of a sequence. Then we have two convergence theorems. First theorem, from first algorithm, we prove that the sequence is strongly convergent to the solution which belong to the common of both variational and fixed point, and the solution x star is equal to the projection on the solution set of f of x star. And secondly, we have a second theorem which show the convergence, which verify that the second algorithm is also strongly convergent and the solution is it belong to the common solution of both problems. Next part, we take one example in, but we have a multiple example here. We take one example where we take a Hilbert space, infinite dimensional space, and convex set bounded by minus 10 and 10, and we have a mapping A, which is A of x, mx plus q, and M is defined is the summation of some matrices, where B defined with the help of K and DK are randomly generated matrices, and T of x is 1 by 2x. So main purpose of this numerical experiment, we study the behavior of each parameter in our algorithm. We will see that how the step size vary, and what is the effect of changing step size on our algorithm, which is experiment one. And then we have a very parameter psi, which used in step size evaluation, and that is experiment two. Then we have first inertial parameter and second inertial parameter, and fifth we will compare our algorithm with the previous algorithms of having the same nature by using different dimensions. The first experiment is about the step size. We have step size we chosen. The first is 2, and then we reduce 1.7, 1.5, and reach to 0.01. We can observe that from a first algorithm, the higher step size provide need more iterations, but the step size which is uh, close to 0.1, 0.2, 0.5 performs better. So we can say that optimal step size is around between 0.1 to 0.8. And similarly for algorithm 2, we have the same behavior, and we say that we can easily to say that we should choose a step size between 0.1 to 0.8. And we have the graphs which verify that these step size behavior. Then we have a parameter psi, which use in the step size formula, and this step size so this parameter belong to 0 and 1. So we take 0.95 to 0.05. So we can say that in the first algorithm, higher the value of the psi provide the better result in term of iteration and in term of CPO time. Similarly, but in algorithm 2, because the both algorithms have different step size criteria, so algorithm 2, the higher value of psi require more number of iteration and more CPO time, which is different from algorithm 1. In experiment 3, this is varying for theta values, which is the first inertial parameter. We can see that there is no much effect by changing different theta values on the number of iteration, but it has effect on the CPO time, and it's shown that higher value of theta require more number of more CPO time. But in algorithm 2, the less value of theta required more CPO time. The last is experiment 4, which is the based on the second inertial parameter, where we can see that higher value of wire theta provides better results for algorithm 1, but for algorithm 2, even for algorithm 2, we have the same, I think, same consequences for both algorithms. when theta is higher, we have better results in terms of iteration and as well as CPO time. The last is comparing our algorithm with previous four algorithms of same nature. We choose different values of m from 5 to 1000, and we can see that algorithm perform better from all previous four algorithms, and even but algorithm 2 perform better in when we have m is equal to 5, 10, 40, 150. But as the value of m increasing, the efficiency of algorithm 2 decreasing comparing to our algorithm 1. So in summary, we present two algorithms, which one is a subgradient extragradient method with viscosity technique, and the second is the Sung extragradient method with viscosity technique. We use dual inertial step size, dual inertial parameters, and then we use different criteria for step size to which is independent of the Lipschitz constant, and also we provide a numerical analysis of the parameters which help to choose the optimal parameter for each algorithm. Thank you very much for listening.